per unit system. Okay, per unit system, basically what we try to do, we try to normalize the value which is simpler and also easier for us in order to analyze our system or our network. The per unit system is very I would say this is a tools that you can use in order to ease calculation your analysis. And quantities of per unit or the value of per unit quantity slightly lower compared to what we have in practical or what we have in our system. So can have one reference, and also all the values in the networks would refer to that particular reference, also known as base value. So here, as I mentioned, per unit quantity is a normalized quantity. We normalize it with respect to chosen base value. And the base value normally being, if in practical, don't know, not being given lah. However, in your questions, in your assessment, whether it's test or in your final exam, the chosen the base value will be given to you, so that all the calculation will be based on what being given, based on the given information. In general, we can say that per unit can be calculated using this equation. We have actual quantity, we divide it with the base value of that particular quantity. Doesn't matter whether it is power, voltage, what else, impedance, admittance, and so on. You can always calculate, normalize the quantity of that particular variables towards the per unit value, or to a per unit value. All right. Here it says here 5 quantities are involved in the calculations. There are current, voltage, complex power, impedance, and phase angle. So if you look at the one that I have in red box over here, this is how we have our base values. Normally for S base or the apparent power normally being given in the question. However, referring to the equation of apparent power coming from voltage multiplied with current. And if we are considering this is the base apparent power, meaning that we must use the base voltage and also the current voltage. But yeah, in most of question, actually S base is given. Okay, this one is given. The one that we try to calculate, maybe this or this one. We try to calculate based on given information. And for the, how do I erase this annotation? Here. Okay. How do I change the size of it? Yeah. Pen tool, pencil tool, is pencil. Okay, pencil. Good. Okay. From the given base information, you can always calculate impedance, base impedance, and also base admittance from that value. From that given information. For example, here we have for Z or impedance, base impedance, actually it's coming from V base divided by I base, and also we can have it like V base squared over S base to find our base impedance value. And for admittance, okay, whether you can invert or flip the numerator and denominator quantities, or you can also straight away, after you get this value, you can always have a reciprocal of ZB, which is 1 over ZB would give us the admittance value, base admittance. Okay. All right, example. Consider we have a transmission line with Z equals this value. We need to find impedance and admittance in per unit. We assume that our base quantities, apparent or complex, our magnitudes of our complex power base value is 100 mega VA, MVA, and also the base voltage, which is 735 kilovolts. Solution will be like this. Okay. Can you see the solution here? Yeah. Okay. All right. Remember that earlier we have Z being given to us, and these two quantities being given. So based on these three information, what we need to do, we need to find this quantity and also this Y per unit quantity. So if you go through the solution, first, I would try to convert it into a polar form. This is the rectangular form, and you must convert it into a polar form in order to get the magnitude of your impedance. Okay, this is actually the actual value of your impedance. And okay, in order to get into our per unit value, we need to understand that the per unit value coming from actual divided by base. So here, you need to find what is the base value of your Z or of your impedance. So here, we proceed with calculation of Z base, where Z base coming from this equation, V base squared divided by S base. So this is the value of our base impedance. And yeah, in order to solve it, to get the per unit value of our impedance, just divide the actual and also the base quantities, and voila, you will get the 0.0143 per unit for your impedance. And for the admittance, actually it's the reciprocal of our impedance value. And if we consider finding base admittance, so we must use the base information of our impedance, and 1 over 8, we will get our base value of admittance. And again, to get the per unit, you need the actual. So the actual value of your admittance, it's coming from 1 over Z, actual impedance, which is 7.37. So this is the value of your actual admittance. And from there, you will can easily calculate your per unit admittance by dividing the actual and also the base value of admittance. And here is the value of your admittance per unit. And yeah, not to forget, this is the first answer and this is the second part of it. All right, and any questions so far?
No, sir.
Okay, I proceed. How about the power flow? For the power flow, it's basically analysis in order to, analyze the powers in our system, in network, power network system. And why we need that? We need it to for future planning. Upgrading our power system, or maybe due to outage. Uh, Maybe there's one of the generator been down, so you need to recalculate back how the power distribution or the power flow in your power system network. So power flow analysis is very important lah. And here are some of the the objective in order to for this particular analysis. We need to know what is the voltage magnitude at each bus. So if later on, that's why it's good if you watch the video before this class, because some of the keywords over here may be new to you. For example, bus. This is not school bus. This is a terminal. Terminal where generator is connected to it. Loads is connected to it. Maybe some of the transformer also over there, and yeah, generator and also load will be connected. Will be connected to this what we call as bus. And voltage magnitude, real and reactive power flowing in each element. Each element meaning that each of the buses, maybe also referring to the transmission line. Okay, real and reactive power flowing throughout the transmission line from point A to point bus 1 to bus B, bus 2, or bus A to bus B. So that's sort of thing that we need to determine. And also reactive power loading on each generator. Basically, this is derivative from this part lah. Actually, if you know what is real active power in each element, it includes also the generator as well as the load. Okay, this is what we have in our power system network structure. And the one that you, a new keyword to you guys is that you have just now is the bus. Where is the bus? Bus is here. Okay, because BUS is bus. Okay, if you see something which symbol, the symbol is like this is considered as a bus. For example, here we have, let's say, 1, 2, 3, 4, 5 bus. And maybe this can also, combine together with this. In some case, maybe. In some case, maybe it's separated and considered as another bus. Okay. Same goes to what you have over here. Maybe you can say that, okay, all this can also be connected to this. Okay. However, let's say this is hydro, right? And the transformer might be located near to the hydro station. And from the hydro station, we have a transmission line. So the one that you see over here is basically the transmission line connecting from the source towards to the load that we have. Maybe this is not the the final load, because you see here we have transformer. Maybe this is a substation, and this substation also connected to another substation over here. Okay, and the final load may be coming from here, where maybe from the substation from 415, you remember that 415 is 3 phase, and reduce it into 240 for the single phase. And finally, this is the final load connected to this particular bus. So this is what you will have in your power system network. So the network structure normally looks like this, and this is considered as a simple one. In the practical or in the what you will find managed by our utility, it's more complex than this. Okay, maybe we have around hundreds of substation, and also maybe numbers of generators, maybe big generators like steam or hydro power plant. Maybe you can also have a generator that coming from the users themselves. Yeah, it's going to be more complex than this. So this is sort of a simplified version of the network structure. Okay, these some of the example as well. If you notice that this is the network figures, and the one that we see over here is also known as single line diagram. So in single line diagram, you have a single line connecting to the bus, and also there's another line connecting to the next bus or the next substation and so on. So this is known as single line diagram or one line diagram, maybe in some of the books. They also pronounce it, or they also consider it as one line diagram. All right, basic step in power flow studies, steps taken to taken in power flow analysis. We have 3 over here. First, you need to have the one line diagram or single line diagram, or maybe in some case you need to have like this network, simple network architecture, so that you have all the information on the connection and also the power rating for each of the bus. And that's number 1. And number 2, we need to construct the bus admittance matrix, or we need to form a matrix from the network that we have from the network, the power system network itself. So to construct the bus admittance, you need to come up with equation. So equations later on typically related to current flow from bus to another bus. In others, I would say that in order to construct the bus admittance matrix, we need current equation. And from the bus admittance matrix, or from the equation itself, from the connections, and later on, we will calculate the power flow analysis equation using these are most popular techniques that we have. We have Gauss-Seidel, we have Newton-Raphson, and also fast decoupled. If you maybe in your higher level, advanced mathematics, you might come across with these names later on. Gauss, Newton-Raphson. It's like a figure, basically, a person invented a way to solve variable, more than one variable, unknown variable, using iteration method. So in this course, in this subject, we're not gonna get into all of these techniques or methods. We will only focus on the Gauss-Seidel method in this course, right? The bus admittance matrix, actually known as a matrix. So we need to provide a matrix, right? So, the matrix itself is known as Y or bus admittance matrix. And as I mentioned earlier, you need to consider the nodes or the what's being connected at the bus. Okay, so the node over here also considered as bus subject. All right. Yeah. Um, it the matrix itself coming from the relationship of voltage and currents, and you know that the relationship of voltage and currents will lead you into a law known as Ohm's law. So what you see over here basically an Ohm's law. So V equals I Z or IR. Okay. In order to get the current, voltage must be divided by the impedance. Okay. And if you think about this impedance being represented in admittance value, okay, where admittance or Y is Y equals to 1 over Z, okay, you can rearrange this equation to become like this, I equals to V, your admittance times the voltage at that particular bus. And why we need admittance? Because we are living in a constant voltage world. Constant voltage world, meaning that the bus, the substation itself, the terminal, bus terminal, not express bus, the power system terminal. Normally, the voltage there had been specified based on the transformer rating, maybe, okay, and based on the application. So we are living in, we can call it as a constant voltage world, whether it's 240 or 15, and maybe other voltage levels. So we will see that the voltage, it's like a fixed value, and the one that we try to play around is the one that changes, have a lot of significant changes, will be the current. And the current will be based on the load that we have, or at our end, what is the our load that we connected to that particular bus or voltage source. So that's why this come into our picture, where we will use the information of V bus, where normally this V will be given, and we will try to set up an equation to get to know what is the current flowing that from one bus to another bus. And the admittance over here is actually can be represented as transmission line losses, or the impedance, can also call it as impedance of the transmission lines. Okay, right. Here's some of the later description on the what that we discussed just now. Nodes represent the bus bar, substation bus bar. Okay, this keyword, I missed this keyword. It's supposed to be bus bar, not bus terminal. Okay. Express bus terminal, not express bus. Okay. Now, branches represented as transmission line, and also injected currents. Injected currents is current flow from one bus to another bus, or from generator to our loads. So here, if you look in this example, not example, in this slide, this is how we come up with the equation of admittance matrix. So here we have three buses, bus number 1, bus number 2, and bus number 3. And we have a transmission line. Here we can say that from 1 to 3. Here we have 1 to 2, and from 2 to 3 or 3 to 2. The value here, line over here, normally can be also represented by resistor and also inductor. Here we have R and also XL, R plus XL here. And since we have Y, meaning that if this is R and this is X, okay, you need to have 1 over R over here and also 1 over X over here in order for you to get the in order for you to get the value of your admittance, or for in this case Y12. Anyway, let's consider the admittance being given. We don't need this 1 over R, except that if this example being given as that over here. Okay, let's consider this one. Okay, I1 over here, meaning that we are considering at this bus bar connection. So at this bus bar connection, you can see that we have connection from 1 to 3, 1 to 2. So that's why you have I1, okay, I1 is coming from I12, okay, plus I13. Okay. Later we discuss on the what happened over here. Let's go to another bus bar. We have connection from terminal or bus 2, 1, and we have 2 to 3. So that's why you have 1 and also 2, 3 over here. And same goes to the other one. We have the last one, which is the third bus bar. We have 3 to 1 and also 3. Okay. Okay. We have 3, 1 and 3, 2. So how do from this line we expand or we further derive our equation? So because our main objective here, we try to get admittance matrix. So here is the equation that we have. Since we have 3 bus bar, so we expect to have 1, 2, 3 equation for this network. And have a look at I12 over here. How do we get this I12? I12 from here to here, you can see here, it's coming from this value, the admittance value, multiplied by the difference between terminal 1 and also bus 2. So we have V1 minus V2 over here to get the current flowing in that direction. I think we also did this in our Kirchhoff current law last time. I mean, the node analysis, if I'm not mistaken, where we have like this. Let's say this is node number 1. Let's say we have a resistor over here. And we have number. Yeah, my writing, because I'm writing using mouse. So if you would like to get the current here, I coming from V1, let's say this is and V2, V1 minus V2, and we divide and we divide it by the value of resistor over here, right? Okay, but in this equation, this resistor being replaced by admittance, where admittance is 1 over the impedance. Okay. If we consider the admittance, we can have the product of Y, or the admittance, multiplied by the voltage difference over here. Okay, the voltage difference here. So here, the first one should be like this. And for 1, 3, remember for 1 to 3, the current is flowing that way. We have V1 minus V3, and the admittance value here is Y13, right? And after rearranging all this, you can see that we have V1, V2, and V3. Suppose that V1 should be multiplied by the summation of 1, 2, and Y12, Y13. And also for the rest will be negative Y12 and negative Y13 multiplied with V2 and V3 respectively. And same goes to other branches or other nodes or other bus. If you see here for I2, I21 is in that direction, so that we have V2 minus V1 over here, and the admittance still actually Y12 and Y12 is also the same as Y21, because it's the same value of admittance that we have over here. All right. So yeah, if you go through all this, and you will end up with 3 equations, as I mentioned earlier, since we have 3 buses in our system. Okay. 3 equations that we have it here, here, and here. And based on these 3 equations, you will, in order to get into the admittance metric, you will try to arrange it into a square matrix, where here, since we have 3 buses, meaning that here we should have like 3 times 3 matrix, where all the components should be here, Y11, Y33, 33, okay, 33 over here, and here we have another values lah, should be in each of the element that we have over here. Okay, this element, I believe Y12, and this is Y13. This is Y21, this is Y22, this is Y23. This is Y31, 32, and 33. So based on these 3 equations, we expect to come up with kind of matrix. So here is the admittance matrix equation, where over here is your Y, here is your I, and here is your V. And in short, we can say this is Ohm's law. I equals to Y times, sorry, not C, V. Should be V. And it is arranged as, okay, based on the size of our admittance matrix. You see here, suppose that the size of I and I matrix and V matrix supposed to be aligned with our admittance, because this admittance matrix coming from equation of I, which also consists information of the voltage. So here, if you do the math, I1 equals to this time this plus this time this plus this part times V3. Okay. All right. You might wonder why we have this one in small letter, okay, this one in small letter, and this one in a capital letter, okay. For the small letter, basically it's the actual impedance or actual admittance value, okay. Let's say I have this Y2 as 2 plus J5, okay, let's say. So here, okay, Y13, let's say here we are 1 plus J1, okay. Component over here should be the summation of these two, meaning that it should give us 3 plus J6, 3 plus J6. And same goes to other elements in this matrix. Yeah. So y, small y, is different with the big Y that we have over here, because big Y, okay, big Y11 is considered the element of column 1 and also row 1. Column 1, sorry, column 2, row 1, column 2, row 1, column 3, row 2, column 1, row 2, column 2, and so on, up until the final column and the final row and column. Okay, are you with me?
Sir, unfortunately not. Can you explain what's the difference between y, small y and large y? Because large y, I don't get the large y part. The small y, I understand.
Can you say it again? Or what's your concern?
What's the difference between what large y again and the small y? That's the part I'm a bit
Okay.
confused.
The small y, okay, the small y is referring to the exact value of admittance, small y over here. And the big Y that we have over here is the total admittance value associated with element of row number 1 and column number 1. And you can also say that, okay, this Y11 actually the total impedance connected to bus number 1, okay, and Y22, big Y22 is total impedance or total admittance connected to this bus number 2, coming from this, and also Y12 and Y23. If you notice that, yeah, Y21 and Y23, this is the total one. And if you look at the big Y for 1, 2, big Y12, basically it's for the first row, second column, and the first row, second column only have Y12. In other words, I would say Y12 is the admittance from bus 1 to bus 2. So it's like we don't have any other admittance connected to it. It's for
I
bus to
see.
bus. Sorry, this is for from bus to bus, and this is for that particular bus.
Okay, sir, I understand now. Thank you.
All right. Okay, if you do some of the if you observe, okay, the admittance matrix, you can see that there's a specific properties for Y bus admittance or the admittance matrix itself. It should be a square matrix, which n, the size will be n times n. N will be number of bus, as I mentioned earlier. Since we have 3 buses, meaning that our matrix should be 3 times 3. And the off-diagonal elements, which is the one that we see over here. This is considered as off-diagonal element. Is negative to each other. And diagonal elements, okay, diagonal element will be the one that we see over here. This is the one that I explained just now. Is the sum of admittance connected to bus 1. Okay, this is for 1. This is the sum of admittance connected to bus 2. And same goes to sum of admittance connected to bus 3. Yeah, if you have this equation, I think you don't need to worry about what are the elements inside these matrices. Yeah, and also the values lah, value. And most of it, I mean, it must be symmetrical. If you're not symmetrical, we cannot consider that one as admittance matrix. You might hit some calculation. Your calculation might be wrong somewhere. Maybe around developing when you try to come up with the equation of your currents. If you notice, this always be square matrix and also symmetrical. All right, example, another example. Okay, in this example, we need to determine the admittance matrix Y bus for given line data. Okay, I just, can we neglect this part, okay, for this course? Because I believe this one, you need to have further understanding about network. I mean, normally, if we include this course will be the third year course lah, third year or fourth year course. But since you are in the first year, enough for us to get to know how can we come up with admittance metric. And another thing is that the line charging subsistence, basically the shunt capacitor connected to the bus. So this is something I think not yet for this course. Maybe if you are major in power system or major in electric power engineering, maybe yeah, I should include lines. And another one, in the load flow analysis later on, normally this line charging subsistence will be neglected. So yeah, why need to get our head, I mean, why need to make things complicated as yeah, we can also always neglect that. All right, anyway, I have the solution for that one. Okay, if we try to answer this question, what things that you need to consider is you need to come up with the admittance value, okay? Because the information given in this table, we have the connection bus to bus, and also we have the impedance, which is R and also X. X over here, okay, normally would refer to value of our XL. And if you combine these two, and this should be the impedance of the transmission line between bus 1 and also bus 2. So this is always XL, and this one is always XC. That's why I think, yeah, forget about it for a while. Okay, how to solve it? I think I'm doing it in the long way. I mean, quite the harder way lah to do it. Actually, there's other style or other strategy that you can use. Here, if you see, I add another column, which is the 1 over R. value and 1 over x value. And when we combine these two, it will give me admittance per unit. And if you combine these two value, R and also X, will give you the impedance unit. So here, from bus 1 to 2, we have 0.004 plus 0.053 in terms of impedance. And for the admittance, 1 over the impedance have its value. Okay. And please note that the question, we don't have any figures, network figures around here. So you have to get in mind how the connection looks like or how the network looks like. So that's why I have this part over here, because I have this part over here to give me some ideas of what I'm calculating. So since we need admittance matrix, admittance matrix format will be looks like this, and we have up to 5 buses, meaning that we should have 5 times 5 square matrix. And also for the current, we should have 5 times 1, and also this is 5 times 1 matrices. In order for us to have a correct way arranging the equation. And how we arrange this equation? Okay, actually this is the answer. And how I do it is by this equation. If you see that from, if I try to find I1, suppose I should find 5 current because we have 5 buses. I1 can be found by looking at the connection of bus 1. Okay? I1 goes to this transmission line times the difference of voltage V1 and V2. So this transmission line admittance is Y12 times V1 minus V2. And there is no other connection, so I stop there and I add the other voltage expression over here as well, so that later on when I put it into my matrix, then it's easier for me to check whether, yeah, this is the correct way to do it. Okay, that's for I1. Let's see, we go to I2. See, I2, we have 2,1. 2,1 meaning that the current is flowing that way. And Y21 basically is the same value as Y12. It's the same admittance value, except that the subscript is slightly different lah. And one is 112, another one is 1, but value itself is the same value. And in terms of voltage difference, since it is 2,1 and the current is flowing in that direction, you should have V2 minus V1 for this one. So V2 minus V1 times the admittance plus, okay, we settle with this connection, plus this is from bus 2 to bus 3, we have this current. So the voltage difference will be V2 minus V3, and the admittance will be Y23. Okay. All right. If you notice that here I have small I, although I write it slightly big, but I consider this one is my small I. So your solution later on, you must clearly show it to me whether this is small I or big I. Sorry, small y or big Y or capital Y. But if you present me with this equation, and then I will straight away understand that this should be a small y, and maybe later on when you set up your matrices, maybe it's a big Y or capital Y. All right, that's the second part. Okay. The last connection will be from 2 to 4. We have current flowing this direction. 2 V2 minus V4 is the voltage difference, and also the impedance, not impedance, admittance connecting from 2 to 4, it's Y4. And again, Y24 is the same as Y42, same. The value is the same value. And we have no connection to bus 5, so we keep it as 0 times V5. And same goes to other equation. If you go through this example or through this equation, you might find, okay, this is how we get the equation. All right, now once you have your equation like this, it's time to put it into your admittance matrix. And this is the admittance matrix that you form based on the equation that you have over here. I'm not going to get into how to form these matrices. I believe I've done it during your A level maybe, or maybe during your secondary school, if you are Malaysian. And matrices also been taught last time. So this is how we, from equation, we form it into a matrix. Okay. All right. And any questions so far? No question? No question. We proceed to our last example. Okay. In our last example will be, we need to come up with one line diagram, sketch a one line diagram, power network from data given. Okay. Remember that the given value over here is the admittance, meaning that this is y, small y, 1, 2, and same goes to the others lah. Small y 13, y23, y24, and y34. Yeah, but in this case, we don't have to come up with the admittance metric, only to figure out what is the one line diagram for this network. Answer would be here, right? We have, let's see, we have bus 1, 2. Here we have bus 1, 2 with negative 2 minus J8. We have 3, 1, 3, 1 over here. Before we sketch this one line diagram, the first thing I would do is I try to have a look at the bus code. What is the maximum value of the bus code? Maximum is 4, meaning that I would have 4 of this thing, 4 of this terminal. Okay? 4 of this. So I need to have 4. And where to put the terminal depends on, it's up to you. If you can also put terminal 4 is over here. But remember that if you put it over here, terminal 4 also connected to terminal 2, then you have a cross line like this. So it's not nice to have cross line like this. Suppose that it should be clear and easy for us to understand the connection. If there is a cross line over here, you might think about, okay, is this the one that crossed the line connected or not? So it's difficult. And maybe you might think about, okay, I would say that, okay, if I draw like this, it is not connected. And it's looks like a funny network graphical representation lah. It's a bit awkward this way. So it's up to you to plan where to put the network bus. But in practical, in real world, it's always we have line crossings everywhere. But in order for us to understand the whole network more clearer or easier, so please avoid having cross line buses. It will make you confused later on. Okay. Yeah, I think for the example number 2, it's very straightforward. It's easy to get this done lah. Provided that you understand what you are doing. Okay. All right. Any question?
No, sir. But sir, if in the case that we are rushing and then we have to draw the line one line diagram, and then we have overlapping, can we just draw it in the form of like how we have circuits that overline, then we just overlap, then we just draw one hump of it. Is it possible to do that?
Mention this problem and suppose you try to avoid it.
Yes.
Okay. It will make me confused later on. Right? I don't know whether disconnected or what. Line crossing. Yeah. It's difficult for me to understand what you're trying to highlight. So better try to avoid crossing line lah.
Okay, sir. Thank you.
Okay. Right. We're done with the admittance matrix. I think the one that really need explanation from me is on the admittance matrix. Once you understand the admittance matrix, it's easier for you to get into the power flow analysis. In this session, I'm not going to get into details on the power flow solution. I just pick up some of the highlights of what you need to know in order to solve power flow. So yeah, you can always refer to the videos on step-by-step of the calculations. Previously, I show you step-by-step because it's very important for you to have the basics of admittance matrix. If not, you might find it, you might not understand the where is this admittance matrix come about. So that's why I focus on the first part slightly more compared to the one that you should revise it by yourself or learn it by yourself. And also, this part basically it's very important in order for you to complete your assignment 1. Yeah, I want you to have an independent study in order for you to learn more about the power flow analysis. But yeah, I will guide you what you need to know about the power flow analysis. But on the mathematics side, I'm not going to get into details on it. All right. Yeah, we know that the power flow will be necessary in order to have economic power network for future planning of failure mitigation and so on. Yeah, it's important. And what we try to do in power flow, we try to determine the magnitude and the phase angle of voltages at each bus. And also, from there, we can also predict the reactive power flow in each line. Okay. All right. The idea is like this. let's say we have a network like this. No, network like this is not good. Right. Maybe this is simpler. Yeah, for me to describe it. Okay. Okay, let's say we have a generator over here connected to this first load. And we know that this generator is like maybe 1 kilovolt over here. And we have a transformer and so on, other equipments, and we see that, okay, this bus terminal will be, the voltage level at this part will be 415 volts. And maybe here with all the transformers, step down, step up, and so on, we have the voltage over here should be 240. Okay, 240 volt. Okay. This is the ideal case in power system. We expect that, okay, all the equipments, 240 equipments is connected to here, 415 equipments is connected to here so that it can functions well according to the voltage level. However, okay, the what we expect over here, 415, 240, is considered without considering the transmission, okay, the length of the transmission over here. How far is this generator to this load, and how far this generator to this load? And since this one or the transmission line is long, and the longer the transmission line, the higher the value of the resistance and also the inductance. In other words, I would say the longer the transmission line, the higher value of voltage will be dropped. Okay. In other words, here without any voltage drop, I would expect when I have 1 kilovolt over here, I will have 415 volts over here. And also I have 240 volts at the bus number 2. However, since we have transmission line, although I have 1 kilovolts over here, this one cannot be 415, cannot achieve 415. Maybe it's slightly lower than this, 410 maybe, okay? Because of these losses of the transmission lines that we have. Same goes to what happened to the 240 bus bar. We never gonna get this 240 because we have the influence of losses of here. Transmission line, maybe conductor, wiring, maybe if you think about wiring at your house, the wire from main source towards your load. So you cannot get these 240 volts, and maybe it will give you like maybe 235, 238 maybe, or maybe 220 for these 240. So this is where the power analysis or load flow analysis is come about, so that we can determine what is the voltage at each bus that we have over here. Okay, voltage at here, we can understand here should be 220 maybe. Okay, once we know what is the voltage value over here, we know that we need to have a higher value of power generated by the generator so that it can match back to the 240 voltage requirement for ideal case. And yeah, to get 240, it's ridiculous maybe, because this impedance is always be there, transmission lines always there, your wire is always there. So you're never gonna get this nominal value of voltage at the bus bar. So in other words, I would say that the power flow analysis, we can quantify what is the losses that we have at the transmission line in order to have an appropriate value of voltage so that our equipment later on works okay. Okay, and what I'm trying to, let's say this is our equipment. I put equipment load lah. I put load functioning well with respect to the voltage at the terminal that we connected with. So that is, I mean, the general idea of why power flow or power flow analysis is conducted, so that the utility or the design, the engineers can estimate the losses due to the transmission and to mitigate the losses or not mitigate. So, like compensate the losses, maybe can generate more power at the generator side so that load be given to consumer will be maintained at its acceptable value. Maybe not to 240, maybe acceptable or suitable for the application of the load. All right. There are 4 quantities that we are interested in of each bus within the buses. First of all, we need to know what is the power, real power, reactive power, and also the voltage information, voltage magnitudes, as well as a voltage angle. So these 4 quantities is the thing that we interest in our calculation. So once we got these quantities, it's easier for us to, I mean, to have the analysis of our power system. And in terms of buses, there are types of bus that we will encounter throughout the analysis. One will be the load bus, where load bus normally the bus is connected to load lah. There's no generator at that bus. Maybe substation can be considered as well. And for the load bus, actually we know what is the our load rating, right? So from that information, we can say that okay, for load bus, we know our power information. We know P, we know Q. Okay, quantity that specified is P and Q. And the thing that we need to calculate is the voltage magnitude and also voltage angle, delta. That's for load bus. And for generator bus, okay, also known as PV bus. PV bus, the quantities that always there, supposedly that we have the active power and also the voltage level. Since we have the generator over there, we will have what is voltage for that particular bus. Okay? So the thing that we need to quantify or we need to calculate is the reactive power and also the angle of the voltage. And finally, this is very important, where our calculation will start from the slack bus. The slack bus is basically the reference bus. Start our calculation of how to call it power flow analysis from the slack bus or the reference bus. And in the reference bus, of course, we will have information of voltage magnitude and its angle, and we consider that one as a reference. For example, we have 1 per unit with the angle of 0 degrees. Okay, 1 per unit. Remember, per unit is a quantity, dimensionless quantity, where the quantity will be coming from actual divided by the base quantity. So when I mention about per unit, meaning that it's normalized value of the voltage or the power or the voltage and power lah. Angle, we cannot have per unit value. All right. For the slack bus, the one that not being specified, basically the power information. So you need to calculate the power information, and the power information of the slack bus, very important, actually will determine what is the losses associated to the network. Okay, associated to the network, the losses in the transmission line. Okay, here are the when we have a typical, this is simplification lah for power system networks. Okay, let's say we consider this one of the bus, and since there is no generator connected to it, we can consider this one as a load bus. Okay, maybe from I1 at the back, you have generator. We can also consider this one as a generator bus, and we can also consider it as slack bus as well. What being highlighted here is this is a typical network connection of a single line diagram. We have single line, whether it is arranged in vertical diagram or horizontal like this, the same. All right. Referring to this bus network connection, we can find the I1, okay, I1 by using the impedance equation. Okay, impedance equation involve voltage, multiplication of voltage and impedance. I think we discussed this one just now, so I'm not gonna get into details how I1 can or II over here II. So we make it general as a general equation. So how we come up with this equation, I think we discussed in detail for this. All right, and yeah, we need to apply KCL in order to get the current equation. Okay, from the current equation, you see here we have admittance value where we can form it into admittance matrix. All right, and in order to get the real and reactive power of that particular bus, okay, you must use this equation where this is a complex power, where we know that complex power coming from V times I conjugate. This is conjugate value of it. So we discussed on the conjugate, why conjugate should be here last time in FOEC. So in order to get a true value of our reactive power, we need this conjugate current information. And you also should understand that this equation or S or our complex power can also be rewritten like this. And based on these two equations, you can gather everything together and come up with this kind of equation or this equation lah. So this equation is very important in terms of you understand the basic of it. Okay, maybe if you refer to some of the reference, the Y that used over here, they use big Y, big Y1, Y11, Y12, big Y. So big Y also, we can use it, but remember that if you use Y, big Y, it's a negative of this Y lah. Okay. All right. Since you see here, okay, there's a lot of unknown quantities that we have over here. Okay, this is considered as nonlinear equation system, algebraic nonlinear equation, and it only can be solved using iterative techniques. That is where Gauss-Seidel, Newton-Raphson method, and also decouple system come across. So the nonlinear equation have to be solved iteratively, meaning that you need to do over and over again in a loop lah, over and over again until you reach the satisfied value of the voltage. Okay, the satisfied value of the voltage is normally being set by the designer, or must be as close as possible to minimum error, or maybe after there is no other changes in terms of your iteration. Let's say you have iteration number 1, V equals to 1. Iteration number 2, V equals to 1.5. 3, V equal to 1.6. See, it starts converge into a value. In this case, it starts to converge into a value which is somewhere around 1.6, something like that. And iterative number 4, it comes 1.61, and iteration number 5 become 1.61, 1.61, 7, 1.61. So it's being converted.
Sorry, sir, I cannot see what sir is writing or pointing in.
Yeah. I'm not writing anything. I'm just
Okay.
explaining about the iterative values. Okay, later on, when you see in the example, you might have the idea of what I try to say here. On the iterative technique, meaning that you need to iterate the value of the voltage until it converges into a stable value. Okay. All right. Yeah. Power flow method. We have for the iteration technique, we have Gauss-Seidel, Newton-Raphson, and also fast decouple. And for the types of buses in power flow analysis, yes, of course, as I mentioned here, we should have 3 types of buses. The first one should be the load bus, where also known as PQ bus, where the known quantities will be the power and active power and also reactive power. And for generator, normally we'll have real power and also the voltage magnitude. And for the slack bus, we always regard the slack bus as our reference, and the slack bus or the swing, but also known as swing bus, will the objective is to determine the losses in the network, losses due to the transmission line, of course. Okay, for Gauss-Seidel power flow, we in this course we only cover for Gauss-Seidel method. For Gauss-Seidel method, there's length of equation, derivation, and so on. You can refer it in reference book, Hadith Sadat. I will share in e-learning. But what I'm trying to highlight here is that after those derivation and so on, coming from the basic of S equals to V I conjugate, you will end up with this equation in order for you to calculate the voltage for the to be used for the iteration. See here we have VI. I means that the bus label. Maybe we have 3 bus. Maybe this is V1. I will be 1, 2, and 3. And you see over here we have K plus 1. K over here is the iteration stage. The first we can start it with k equals to 0 and increases 1, 2, 3, and so on. And yeah, other things, I think that's normal, and also we seen this before. Okay, another one is the SCH. What does it mean, this SCH? SCH means scheduled power. Scheduled power meaning that the power that been given in the question. So if you consider bus type over here, okay, this is considered as a specified value and also considered as scheduled value. Okay, PSC is the scheduled value of SCH. It is scheduled value of whether it's real power or the reactive power. Okay. And another thing is on the here. Why J not equals to I? Because if you have 3 buses like this, okay, 3 buses. This is bus number 1, number 2, number 3. If you choose I as 1, 2, meaning that this J over here cannot be 1. It should be either 2 or 3. And 3, not 2. 2 or 3, or 2 and 3. All right. Line flow losses, yeah. After the iterative solution of the bulb voltage, actually the iterative part is to get value of bus voltages. Okay, next, you would like to compute the line flow and line losses. And in order to compute the line losses, you need to have this value of current. I mean, the current from bus to bus, okay, current flowing through here. And of course, if you consider like this, let's say from V1, let's say this V1, this is V2. Okay, here I should have I12. Okay, I12 equals to IL that I have over here plus I coming. Oh, okay. I cannot use this equation. All right. Never mind. Actually, this IL plus I naught, I naught, I naught is I12. What is I naught? I naught, okay. This one is the current at default value. Okay, initial, default or initial. Or maybe initial. Okay, this one is the current. Okay, so since we are doing iterative strategy, meaning that we're going to have initial and also current. And this one is the true value of I12. Okay? The current plus initial value. All right. I think I'm going to skip this one. We straight away go to the example and see what are the important element that we need to know in order to solve using the Gauss-Seidel. And consider this is the example. You can refer it in my reference number 5, Hadis Sadat, page 212 to 216. Yeah, I believe you never get into this page before this lah. Okay. Based on the question, it says here that figure below, where is the figure? Oh, here. Okay. figure below show the one-line diagram of a simple three-bus power system with generation at bus 1. Okay, here see that we have a generator at bus 1 and also consider a slack bus later on in question. The magnitude of voltage at bus 1 is adjusted to 1.05 per unit, meaning that over here it is given the voltage level over here is 1.05 with the angle of 0. So we have two information being given. The first information is the voltage magnitude. The second information is the angle of the voltage. The same with what we expect earlier in the slack bus. We expect that we're going to have voltage and also the angle being given to us. Right? Okay. Go on again. The scheduled load supposed to be load at bus 2 and 3 are marked on the diagram. Schedule load. Schedule load. What is schedule load? In this case, schedule load is this value. Okay. And this value. So here we have two buses which considered as a load bus. Okay. You see here for load bus, we have the information of P and we have the information of Q. Same goes to here. We have P and also Q. And looking at the sign of the reactive power, it should be a positive reactive power connected to the bus number 2 and also bus number 3 because it's positive. XL, I would say. All right. The line impedance are marked in per unit on 100 MVA. Okay, what is this 100 MVA used for? Actually, this is your S base. Okay? Your S base. Okay. Yeah. Again, and the line charging susceptance are neglected. Okay, line charging susceptance, the one that you see in earlier example that we neglect the value. So this value always being neglected in power flow analysis to make our calculation more simpler, but not that simple lah. It's a bit complex. Okay. Once you understand the information given to you, okay, the first one is the slack bus. Okay, the bus with the generator. We consider that one as our slack bus. And please remember that if you make that bus as your reference, meaning that this information is the magnitude and the angle will be regarded as 0 degrees. Okay, we put it as our reference unless it being specified. If not specified, then you can put it as 0 degrees angle as your reference. And other things that you need to understand that line impedance are marked per unit, meaning that you don't need to do the conversion from its original value into per unit value. However, okay, here it's been given as a line impedance. If you want to proceed with the analysis, this one will be converted into admittance or Y. So this is considered as Y12, but not this value. Okay, Y12 should be 1 over Z12. So given over here is the impedance. So here should be the Z12, not Y12. And when you try to solve it, you solve your network using power flow analysis, all these values should be converted into admittance value. So 1 over Z being given the per unit. All right. I have the solution of here. also being shared to you in the lecture notes. So I want you to go through this example, okay, and try to understand what's going on in terms of using the Gauss item. I think the information being given to you quite I've guided you on how can you get into analysis, but I want you to experience yourself doing the calculation and doing the maybe later on in your assignment you need to do the simulation. Okay. If you look at the assignment question, where's the assignment question? It's here. Okay. If you look at the assignment question, part of it have been solved. Okay. You see here the table that I have over here. Okay. In your assignment, you can also neglect this part. Maybe later on I will inform e-learning. I will put slash over there where you can neglect. If you see the assignment one, part of the solution, get discussed. Okay, it's up to you to get more information on how to solve question number one and also to complete question number one and question number two. So here, I would really suggest you see example in Hadi Sadat book lah. So we have two example over here. Hadi Sadat book is reference number 5. Looking at the your e-learning portal. If you look at e-learning portal, you might find Hadi Sadat book. All right. What I try to explain here is that first thing, okay, you need to convert into admittance as we discussed. Once you get it in admittance value, you can also redraw this figure, example figure 6.9 into this figure for that, so that you know, okay, I'm working on all these values. Okay. And looking at the solution, the first part will be solving using Gauss-Seidel method, and as I mentioned earlier, for the Gauss-Seidel method, our objective is to find the voltage at other buses. In this case, voltage at bus number 1 or the slack bus is given as 1.05, and we need to find the voltage at 2 other buses over here and also over here. And the way we find the value of voltage is by doing the iteration process. Okay, this is how we conduct the iteration. Okay, I'm not gonna get into details on the values over here. I just highlight you, this is what you should expect in your solution, and this is the process of the Gauss-Seidel iterative methods. And yeah, the first one is converting the admittance. The second one, okay, the second one, you see here our information of P and Q, it's in original value, okay, it's true value. However, here we have a per unit value and the slack bus also given in per unit value. And the next thing you need to do is you need to convert these 4 quantities into a per unit value. So that's why you have this line. Okay. And once admittance is there and your per unit for power information at bus 3 and 2 been converted into per unit value, you can do some initial estimation on what you will expect in terms of value of voltage over here, V3, and also voltage over here, V2. And the best way to start with is by taking initial estimation of 1 per unit value for V2 and also V3. So here, that's why you see V2 initial, V2 0 is 1 plus J 0. It's same as V2 is 1 per unit and V3 also 1 per unit for initial value of V3 and initial value of V2. And why this initial value is important? Okay, let's say we consider the first iteration. For the first iteration, we consider K equals to 0. Okay, so based on this equation that we have over here, K should be equal to 0, meaning that we need to find V2 and V3 0. V2 0, V3 0. However, since the thing that we want to calculate is at V2, so in this equation, we don't have V2 lah. We only have at the one that we want to calculate as V2. So towards the end, we don't have any V2 0 over here. We don't have it. However, if we have like other connection, okay, let's say we have another connection over here. So let's say this is 4, meaning that over here we need to have V4 not, or we need to include V4 in order for us to calculate V2. Okay, now K equals to 0 and I, since we are calculating the second bus, so I should be 2 and J should be 1 and also 3 in this case. And this, I mean, in this case, J coming from the slack voltage and also coming from the initial estimation of V3. Okay. All right. I think you understand, and the symbol over here, we have the symbol of like this. This is assumed as sum. Sum. So that's why you have sum over here, and you have the sum over here as well. Okay. Okay. In some books, this I should. I think we extend a bit in terms of my class today, because this is maybe the last part of it. Hopefully we can finish it here. Okay, in some case, this formula in some book, it put it as minus, but this is okay. It's okay. P minus J QI SCH is always negative over here. However, you might find that in some of the reference, this being written as minus. The question is that, is it the same as what we have over here? The answer is the same. Remember, okay, remember, let's here. About the admittance. Where is it? I put it. Okay, remember over here. Says that y, big Y, equals to negative small y. So now we are using small y, and the sign is positive. In order, in the other reference, we put negative, they will use big Y over here, big Y. Okay, it is very maybe you might find it confusing lah. But if you follow Hadi Sadat book, please follow the technique that the book suggests lah. So now the book suggests that we use plus over here, and you must use a small y over here in your calculation. So will be safe lah. If you mess up with small y, big Y, as Riff asked just now, I think what Riff asked is very good question, so that you will know the difference between big Y and small y, capital Y, small y. Okay, once you get into the set up the equation, okay, you will get the value of your V2 as, okay, V2 first iteration, V21 equals to this value, okay, and you have to use this value in order for you to calculate for V3 first iteration, okay. I would say that you must do it one by one. The first, we know this value as V1 as this, 1.05 with angle of 0. And we go through the system. We calculate this one, V2. Okay. And V21 have been calculated over here. And this V21 should be used to calculate this V31. And go around the system. And of course, since this is a slack bus, V1 first iteration, V1 second iteration, and how many iteration that we have, V1 will always be in the same value as what being specified earlier for our reference. So V1 never change. The one that change is the V2 and V3. So you need to do it iteratively around this network. So first, start with the slack bus, go through the system into V2 and find another voltage at another bus bar connected to V2 and go around the system until you reach back to the slack bus. And you repeat the process iteratively, meaning that until the value becomes acceptable or becomes what you desired lah. All right, this is the process for V3 first iteration. And for the second iteration, you see here, we'll use the value of V31 over here. And here we have V1 or the slack bus, V11. Okay. And to calculate V2, V3 second iteration, you see the one that you have over here, 0.9816 is the value of your V2 that you calculated earlier in for bus 2. Okay. And again, this should be fixed as your slack bus or as your reference, for your reference. And the process will be continue, blah, 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 until the accuracy comes into acceptable. This is always being given later on based on the what given in the question. Let's say accuracy is 5 times 10 to the power of -5, meaning that there's no other changes between the first and also the second iteration or the third or fourth iteration. There's no changes in the iteration. Okay, and we stop it. And based on this question, it says here until the seventh iteration, okay, until the seventh iteration, we stop because we see that there's no changes, okay, in terms of voltage level at V2 and V3. So we stop. And if you further iterate into the 8th iteration, you might find you will get the same value over here, the same value. So in this textbook, it never mentioned on that one, but you can always try for the 8th iteration to prove that, okay, until 7th iteration, the solution is converged towards our specified accuracy. Okay. In other words, I would say it doesn't matter lah. Maybe in some cases, I would say last time during my time as a student, I received this question and it says here, do the Gauss-Seidel analysis up to first iteration only. So actually, the iteration is like try to guess what is the value of voltage at that bus bar or at that connection. All right, we skip that one, and once we know this is our answer, our voltage level, and we can stamp it as our final solution for V2 and V3. And actually, the Gauss-Seidel will ends over here. A Gauss-Seidel actually try to do the iteration part to determine the voltage level. And the next part will be finding the power flow, okay? And to get the power flow information, you must start your calculation or your analysis from the slack bus, okay? From the slack bus, because the slack bus will give you the information of power and also losses of your system. You see here from the example, other buses, we know the power here, the power over here, scheduled power over here, except for this one, right? So this is the one that we want to determine. What is the power over here? And from the power over here, we can know the flow of the active and also reactive power. And to calculate the power at that slack bus, you will use the information, or you will use this equation lah. Maybe later on you get into Hadi Sadat book and how this equation come across. So in general, I would like to say that after we determine the voltage, we determine the power at the slack bus. Slack bus is like a reserve bus lah, a reserve bus where the power is yet to be determined and will be determined based on the voltage level. Once we get all the voltage level at the buses connected to it. So in this case, buses, we have 3 buses. One we know over here, the voltage is here. V2, we just determine using Gauss-Seidel, and V3 also we get it from Gauss-Seidel. And the last part will be coming into information of power at bus number 1. So this is how we calculate the bus power. And from the power that we seen from the slack bus, you see here, we have calculated, since all of this in per unit, we have our final answer also in per unit. And to know the actual value, you just multiply with the base value. You see, last time we know that if we have Z per unit, it coming from actual divide by base, right? Okay. Okay. Based on this information, you know the per unit value. You know the base value. The base value will be 100 MVA. And what you don't know is what is the actual value. So here, how do you get this 409.5? You multiply this with 100. Because 100 MVA is our base complex power given in the question. All right, and once you get the power, and actually you can also, since you know all the voltages, actually you can also calculate what is I12, I21 is the negative of I12, I13. This is all coming from the one that we practiced in our example just now. The equation that we set up at each of the bus bar, and also current flowing through in and out of the bus bar. So once you know the current flow, then you can estimate what is the power from bus 1 to complex power from bus 1 to bus 2, where you can use this equation V1 times conjugate of I12, and this is the power that you have, and same goes to 21, and please note that although one I12 and it's actually negative of I21 is negative of I12, okay, we can say that. However, when you put it in the influence of the voltage here, the power information flowing from 2 to 1, slightly different. Slightly different. Here you see that for S12 we have 199.5. Here we have negative 191.0 megawatts. And for the reactive power, we have 84 megavars, and we have negative 67 megavars for S21, or when we refer the current flowing from bus 2 to bus 1. It's different. Although the current value is just a negative, but since the influence of the voltage here, it will result us towards different value of complex power flow from bus 2 to bus 1. Okay, if you go through this, you can see that the net complex power is the summation of these two complex power that we calculated earlier. One is from 1 to 2, another one is 2 to 1. Let's say I put it over here. Right? This is 2, this is 1, this is 2, this is 1. 1 to 2, and this one is 2 to 1. And you see that this is the difference between those, you're getting the net value of complex power. And here are some of the description indicate the flow of the reactive power, and also, this one is for real power, and this, when we have like this, is the indicate the direction for the reactive power. It's easier for us to see over here. Okay, using the voltage level, once we got the voltage level, we can get the slack bus power information. From the slack bus power information, we can calculate the current. Basically, not from the slack bus information solely. You can also, since you have V voltage level at here, voltage level at here, and also voltage value over here, you can always calculate the current flowing through here, or either in this direction or in the opposite direction, where we consider from 2 to bus 1. Once you get the current, you will straight away calculate the power information from that particular connection. Let's say for the one that I circle over here, from 1 to 2 is 199.5, and reactive power is 84 vars. And from 2 to 1, we have 191, and reactive power of 67. And the one that you see in the middle over here is the difference, or the net value of your complex power. The net value of complex. Same goes to over here and here as well. All right. So that's the objective of doing the power flow analysis. You want to know what is the difference or the losses. Basically, the one that you see over here is the losses. This is the losses, this is the losses. Power loss, okay? Power loss. And if you see, you have 8.5 watt losses when you try to transmit 199, and at the receiving end, you have 191 power can be used, and balance is losses around the transmission line. So to know what is the power over here, this one, the load demand plus the losses will give you the value supplied the network in the connection between 1 and 2. Same goes to other connection from 1 to 3 or from 2 to 3 as well. All right, I have also another example, but I think yeah, it a bit trickier compared to what you've seen over here. And I believe the one that you see here also complex. You need time to digest. Yeah, I give you time. And for the example 6.5, maybe you can use it in order to get the understanding of this example in order for you to complete your assignment. So I think that's all for today. Okay.